开场我是用中文哈，因为请大家自我介绍，完毕之后我们就全部用英文，这样可以吗哈？这样，所以你用英文讲没有关系哈。那就请各队先自我介绍，从今天的我们的 reporter 这一队哈，big long pair， 请自我介绍哈，队长介绍自己跟队员。
Hello, we are the team Big Long Pair and come from KSHS. And this is Benjamin, and this is Ryan, and this is Rebecca, and this is Little. Okay. And I'm Harrison, and thank you. Good luck for today's competition.
Okay, thank you. All right, 今天第一回合的 opponent， 是 MDHS， 自我介绍。
Hi everyone, we are MDH, S501 from Middle High School, and I am Wu Hongru. He's Chen Yujin, he's Lin Yueli, he's Tong Shaoqi.
好，第一回合的 reviewer， Miracle。
Good morning, everyone. We're Team Miracle. This is our captain, Tim Chen. I'm Ren Jingyang. This is Ri Zheyan, and this is Chen Hetian. Hope you enjoy.
OK， 好，那我们就请老师自我介绍哈。那我先自我介绍，我姓甘宏志哈。那我是从中正物理系在嘉义。那这一次是第一场到这边当评审。OK。
大家好，我叫陈永富，那从中央大学物理系。
大家好，我叫杜启勇，是中原宇宙物理系。
各位好，我是从台湾大学来鲁教白位路。
各位好，我叫季文，从中原大学物理系。
Okay, so thank you. We all introduce ourselves. So we'll start our first round, right? Okay. So the reporter is Big Long Pair, and the opponent is MDHS. So the opponent can challenge the reporter.
Loud voice.
Okay, you got 1 minute response. Clap.
Reject.
Reject. The reporter reject the challenge. So opponent.
Number one.
All right.
So
Are you okay? Yes.
number one, reinvent yourself.让他讲他的继续。对，他的第一分钟过，但他还是要讲。So. Okay, so the reporter accepts the challenge. The problem is number one, reinvent yourself. Okay, so we'll reset the clock. Okay. Okay, so the reporter, you have 5 minutes to prepare.
Okay, I'll sign for you.
Question number 9, soy sauce on rice and number 8.
Okay, have the reporter, opponent, and reviewer write your name on the board. The reviewer, you have to write your name on the board.
Excuse me. Now the voice is question number 7.
That voice is question
Number 7, not
it's
question
number 7.
Yeah, number 8 is sci-fi sound.
Yeah. So they reject number 7.
Yes.
Thank you.
Okay, number 7.
Thank you.
One voice, number 7.
有没有想好客套话？这个是最重要的。对，昨天到A，刚刚至少客套话最好了。
Okay, the reporter takes the floor. You have 12 minutes.
Okay, hello everyone. Today, I'm glad to be today's reporter and hope you enjoy my presentation. And for question number 1, invent yourself. For the carbon statement, this question wants us to build a model that's published based on the Coronal discharge. And we have to use the fixed voltage to let it can turn the fastest. So let's do it. For the what is Coronal discharge? And Coronal discharge is when electrode have a sharp tip and it have a high potential, and it can have the coronal discharge into the air, then have ionizing the air around it, and then the electron can be into around the air in that. And if it have a short point, if the electrode have a short point, the electric field can be higher than other way. So it can be easier to have the coronal discharge. Okay. And coronal motor is a kind of electrostatic motor, and it is based on the electron, and it uses the attraction and repulsion to let it turn. Okay. Okay. For the topic number 1, to build a simple coronal motor, and material, we need these plastic bottles and perimeters. Its width is 7.2 centimeters and its perimeter is 23 centimeters. And the foil tip is for tape stepping on the bottom. And then it's the center exit, and we need a plastic tube and a bedding to let it can turn smoothly, and a Winston machine to start the coronal motor. And then it's some tin foil to tape on the electrode, and the iron wire, and the cord clip. And other is I use the cell phone to take the photo, take the video and photo for this experiment, and knife and tape something. Okay. To build a simple coronal motor. Okay. For the coronal motor, because it is a static motor, so we need to input the electrode into it. So we need the Winston machine, and this is the Winston machine. And this is my coronal motor in the experiment. And in my experiment, the electrode and the coronal motor is the space between them is 2 millimeters. We use it to do my experiment. And for the Winston machine, because we need a fixed voltage, so we have 2 RPS for the spinning speeds to let the voltage to be fixed. Okay. And this is the video of turning. Okay, and you can see that we turn the Winston machine, and then the coronal motor can be. And topic 2, to explain how it works. Okay, for the explaining. Okay, first, for the electrode, negative electrode, it will have the negative charge on it. So in the first step, then it will, because it have the sharp tip and it have a high potential, so it will have coronal discharge around the electrode. Yes. So then, because of it, so the negative charge will go into the air and go onto the foil on the bottle. Okay. The next is the negative electrode will repulsion each other, so it will base the foil to move. It will base the foil to repulsion from the electrode. A is the negative electrode. Then the positive electrode is electrode B in here. So because it don't have the negative charge on it, so it will attraction it. So it will turn to the positive electrode. Okay. And then the negative charge will go onto the positive electrode. Okay, then use the Winston machine. It will remove the positive electrode from the electrode B and negative charge from the electrode B, and then add the charge into the electrode A, and then repeat these steps, and it can work like the Coronal motor. Okay, and then is my experiment. For the first experiment, I used the tin aluminum foil to tape on it. So I need to decide to tape it inside the rotor or outside the rotor. So so you can see that if I tap inside the rotor, it can turn, but maybe the video isn't so clear yet. Okay, and if I put outside the rotor, it can't turn. So why is it happen? Okay, for our explain, it's because if we tap inside the rotor, the resistance is high. The resistance of the plastic is really high, so it can be the high it can go on to the high voltage to let the Coronal discharge to be enough strong to push the rotor spin. And then if we put in the if we tap the tape outside the rotor, it has not enough resistance. So when the voltage is high enough, it will first have the breakdown voltage. So the voltage will be come down again. So it won't be enough. It won't have enough Coronal discharge in even any time. So it can turn. For the next, the second experiment is the distance of between the electrode and the middle of the rotor, and we have few different distance of it. This is 4.5 to 7.5 centimeters, and we know that the 6.5 centimeters have the fastest spinning speed, and for 4.5 and 7.5, it even have stopped on. So we know that the best distance of them is 6.5 centimeters. Okay, and this is the video, and for that one is the 4.5 centimeters, and it can turn, and this one is 6.5 centimeters, and it can turn it can turn really fast, not yes, and this is even stopped. So okay, this is stopped. Okay, for the result, because if the electrode is too near to the rotor, the angle between the rotor and the electrode is too small. That because Coronal discharge will let the electrode between in the air for around the electrode. So if the angle is too small, that some electrode will be over into the air and can't be catched by the rotor, so that it can have really large energy for it. And if its degree is too big, like if the distance of it is 7.5 centimeters, the angle of it is nearly to 90 degrees. So it's the way of the electrode pushing is different to the rotating way, so it will do really less work on it, so it even can't rotate fastly. Okay, and if it is 6.5 centimeters, the degree of them is 75. So we know that this can let it turn really faster. And these are, I put the different way to the electrode. Is like I put 4 electrode, and for the negative and positive one is in each other way, and this one is in the near way and near way. And Q1 is I put the different side of the rotor, and this one is put the near side of the rotor. And we know that the 2 is near, we put 2 electrode can rotate fastest. And then is the angle of it, because we know that 2 electrode can rotate fastest, so we put the different distance of these 2 electrodes. So we know that the 190 degrees is over the different side of the rotor can rotate fastest. Okay, and these are, I put different amounts of the tape on it. And we know that this one is, I put 2 electrodes, and I put 12 pieces of the tip can rotate fastest. And so the result, we know that we put...
Okay, you have to stop. It's 12 minutes already. And 2 minutes for question and from the opponent.
Hi everyone, my name is Wu Hongru from Minda High School, MDHS 18. And first I want to ask the reporter, do you measure the attractive force and the repulsive force on the cap of your motor?
This is I count of the number of the...
Yeah, measure it.
No, I didn't count of the number, but I count of it can affect its spinning speed. Yes.
Okay. Then, do you observe the electric arc in your experiment?
Can you explain?
Do you observe the electric arc in your experiment?
For the machine.
Yeah.
Machine.
When it is moving.
What? I don't understand the...
Do you know the electric arc?
Sorry,
it means some glow between the conductor. Yeah, some glow between the conductors.
Oh, because of the plasma. It will have the plasma of the electric arc.
Also, you did observe the electric arc in your experiment.
Yes.
Yes. Can you show your experiment video?
Because these videos are really small, so
Yes.
maybe you can really clearly see those on it. And because of when the electrode is negative charge is really fast on so we can't really use the cell phone to take the video or photo. So.
Okay, time's up. Okay. So the opponent have 3 minutes to prepare. Okay, opponent takes the floor.
Okay, and this is our PPT for the problem number 1 event yourself. And this is the problem statement. And this is some summary for the reporter. First, their theory is point discharge, and it will ionize the gas. So the electric charge will go on the cup and make the cup rotate. And this is their experiment. They use generator, cup, and foil paper, and some electrode. And their parameters is distance between the electrode and the cup. Also, the electrode position will affect their results in the report. And this is the reporter's advantage. And they have the clear explanation for the phenomena. And they describe the cause and effect in very simple way. And their PPT is very good looking. But their words is, I think their words is too many in the PPT, so I can't watch very clearly what the PPT wants to talk about, but his speak is very fluent. And this is some advantage and suggestion for the setup. The setup catch the main point of the problem because they really use the Coronal discharge and it really works. Okay, and now I want to ask some questions to the reporter. First, how do you measure the efficiency of your motor? Efficiency. Do you measure the efficiency of your motor?
So you are moving to discussion now?
Yes.
Okay.
Well, I want to go to a discussion.
So thanks for the opponent's question. So the question is.
Do you measure the efficiency of your motor?
Because we use the machine to let it turn, right? So
yeah.
We have the machine and it can we control to turn the machine in 2 rounds in 1 second. So we think that this can have the measure.
So what is the maximum efficiency you measure in your motor?
Okay. So how to make the fastest motor?
Yeah.
Yes. In my experiment, I used 12 pieces of tape on the rotor and to let it turn, and it can turn really in really high speed, like 14.6 rounds in a second. It is really fast. So
May also depend on the voltage you input, right?
because I turned the machine in 2 rounds in 1 second, so maybe the voltage will be the same as every experiment.
So how much is your input voltage?
Input voltage. In the count of it, because this Winston machine and I search for the data is it will have the breakdown voltage and it is really high, about 300,000 about. So maybe it is really high and I can't use the the machine to test it because I used the machine to test it and it can't work because it is really too high and just.
Okay, and why do you put the foil into the paper, into the bottle? Because it means
Yes,
that
yes.
the electrode is cross the plastic cup
And
and go into the foil.
yes, because it is used the Coronal discharge, so not just through the foil. So I put in it is because I need the high. I need a high resistance for it.
You want a high resistance.
Yes, I need a high resistance that it can have a high voltage to let the Coronal discharge to be really high. That can let many electrons in the air then catch by the tin foil, catch by the foil.
So the cup, the electron will go on a cup, and through the cup it will go into the foil.
First it will go into the air because it is the Coronal discharge. Will let the electron go into the air, then it will be the yes. Then it can go through the cup into the foil. Yes.
Okay, so you think the gas will be ionized is because the voltage is very high.
Yes.
Okay. Then, if the gas really be ionized, you should see some electric arcs in your experiment.
Right. Actually, we can see the little bit, really little the light of it. If we close up all the lights and close down the window, and we can see a little bit. But if in this, if like this, we can't use cell phone to take it because it is all dark. So, and its light is really a little bit, but it have a little bit art of it. Yes.
Okay. So you think the plastic can be a conductor? Yeah.
No, it's not. It can a little bit conduct, but not a really good conductor. So it can let the resistance be really high. So yes.
You say the
Or-
plastic cup isn't a good conductor.
Yes.
Then why you put a good conductor like foil paper outside the cup, but it don't work?
Yes. We think about it for a long time, and we find out the experiment. In my experiment, I don't know if this can show to everyone because the video is really small of it. Because if we see really near to the electrode, it will have the electron over just like this. And we search for it. It is called the breakdown voltage. So just like maybe lightning like that, this and it will let the voltage to be lower, just because and the voltage will be down to the really low voltage. So it can let the Coronal discharge to be really high, output the electron into the air. So maybe it can't work. This the reason.
Okay. Then can you explain your data?
Yes, data.
What why the nearest distance will stop the cup?
Okay, first I want to explain the distance of this because this distance is the end of the electrode and the middle of the rotor. So it have a distance and add minus the distance of the rotor to the middle to the foil, and then the electrode have a distance is 3 cm, so it can count out the angle of the electrode and the rotor. So
what do you mean the angle between the electrode and the rotor?
okay, and can I draw the picture? So this is like this one, and the distance of those is the middle of the rotor. This one is rotor. So the middle to the end of the electrode is here, and this one is the electrode. So electrode is 3 cm, and this one is about 3.6 or what? Okay, and this one is the distance of that. So we can count off the distance of this angle. So of the distance of 4.5 centimeters, the angle of it is really small. That it is almost can let all the electron in the air to go onto the rotor. So it can't let it turn really fast. And if the distance is really like 90 degrees, because the force of the force from the electrode is different. It's 90 degrees to the rotor spinning friction, and so it won't do really many work on it, so it will turn really fast. It won't turn really fast.
But if the distance is small, the voltage will be higher, right? The electric field of the cup will be higher than the long distance, right? Because we know the electric field is
Maybe
is divided by the distance squared.
No. The distance is the maybe I should change the distance into the angle, but I just count the 6.5 centimeters is the 75 degree, and others I not yet count these out. So I know that it's not the degree of the tip of the foil of the electrode and the bottle. It's the end of it. So it will have the triangle of it to let it can control the angle of the electrode touch the bottle.
You can write on the
Yes. Maybe I should explain it yes clearly. So this is the bottle, and this is the electrode, and you see the distance of it is from the end of the electrode to the bottle, the middle of the bottle. So it will have an angle of it, because if the distance of the tip of the electrode and the bottle is, I control it in 2 millimeters, so I won't change it because it will affect it really much. Like if fire will be really slow, that can spin. So I control. So this one is actually control the angle of here. So yes, the angle of the electrode touch just near the rotor.
Okay.
The angle of here. Yes.
And finally, I want to ask, did you have a function or something can describe your experiment? Function. Test.
I just found out the.
Okay, time's up. The opponent has 1 minute to summarize the discussion.
Okay, during this discussion, we know that the parameter is the distance between the cup, middle of the cup and the electrode. And this distance will also affect the angle. But the main idea is the angle between the electrode and the cup center. So they also found that if the distance is in a certain range, the speed will be fastest. Yes, and I think they really did a good job on their experiment because they seems to do very many experiments, and despite their video is very small that we can't clearly see.
Okay,
That's
so reviewer, you have 3 minutes for questions.
Good morning. First of all, the reporter, I would like to ask you if you observe about the engine, right?
Yes.
And is the angular velocity stable?
Yes. Which one?
Angular velocity.
Yes.
I mean the machine itself, not the
Yes.
not.
Because if you spin it in the same speed, it will have the same angular
Velocity.
Yes.
And second, I would like to ask you if you discussed any parameters in moment of inertia, such as the mass of while it is turning, such as the mass of the bottle. Did you discuss it?
Yes. I count of the those. It's really I control it in the same amount.
Same mass,
yes,
right?
Yes.
So you didn't did any other masses.
I did it in a bigger bottle, and it is quite different about them because if I put a bigger bottle, it can let more electrodes on it. So it is really different, and yes. So
How about radius? The radius of your bottle while it's turning, right?
yes.
Due to the opponent, they got an attractive force.
Yes.
Then you use a force to pull a rod, then the rod spins, then the radius occurs.
Yes.
The radius influences. And did you discuss a radius?
It's sorry, can you?
The radius of this.
Yes.
The radius.
Yes. Yes. Because when I change it to the bigger bottle, it will spin more slower because it have a bigger mass and a bigger.
Pure inertia.
Yes.
Thank you. And you discussed about if the plastics is conductivity, and so I would like to ask you if you change the materials.
Yeah. Which.
The bottles, those plastic. If you change plastic into other kind of plastic or etc.
Oh.
Do you change?
For one time I just because in the experiment I put the tape outside the bottle. it can't turn, so I don't know why and I put
So let's discuss if the bottle is more conductive, then
Yes.
you think it will be faster or slower?
the bottle
Yes, the bottle more conductive,
more conductive,
faster or slower?
faster. But if it is
Okay, faster. Okay, and how about
okay.
Another thing, faster or slower?
Well, I think it's more conductive.
Okay,
more fast.
reviewer, you have 2 minutes for preparation. Okay, reviewer, take the forward. You have 4 minutes.
Honorable judges, ladies and gentlemen, good morning. I'm the reviewer of Team Miracles. Today, I would like to review problem number 1, image yourself. And this is a problem, and I think the most crucial point is the first Coronal charge, and we have to have a maximum speed at fixed voltage. And this is a reporter's outline. They have a nice but not clear enough file. It's a bit small. They have a clear but not nice but not clear enough setup. And their theory have clear explanations, not quantitative. And their experiments is very deep in angles, distance, such these things. But I think it's not enough. There's not enough parameters changes. And the conclusion is incomplete. And here are the reporter's pros and cons. They have nice explanation and nice animation, which is very clear. But they have not enough parameters and not quantitative theory. And opponent's pros and cons is discussed about the theory. They are very clear and neat about the presentation and the speaker itself, and they have crucial basic problems that affect the theory itself. But they don't have the crucial problems that actually discussed in the RIPT's problem itself. And they didn't discover that there are lots of parameters didn't discuss. And first, they discussed about voltage and forces. The opponent asked if the fixed voltage is measured and if the attractive force is measured. The reporter says that they didn't measure these two things, but they believe that this is fixed. And my opinion is, if measured, then it is better for us to do quantitative experiments. So I would suggest them to measure it. And they discussed about the electron travel, while the opponent asked how the electron crosses over the plastic. The reporter thinks that it travels enough fast, so the opponent thinks that the corona should be observed. The reporter says yes, but they can't take the photo. And they asked about the conductor's problem. The reporter started to talk about breakdown voltage. I don't agree with the electron travels faster this opinion, and I think they should do more materials experiments to solve this question. And excuse me? Previous page. And this page. Next. And I asked about angular velocity, and they discovered it's stable. But I think that this needs explanation, while their theory is repulsive force and attractive force, but there are no any quantitative data that shows why it has to be stable. While these two forces varies when the ball is turning. So I think it can do more work on this. And after about the Coronal and inertia, they controlled, but they didn't consider it as a parameter. I think that the report itself, also said that they use bigger balls and it turns slower. I think that mere inertia makes it slower, while the force may be stable. I don't know, but this needs more experiments. And this is a missing point that between the discussion of reporter and opponent. And then I asked about the materials of all they inspired me that the problem of the capacitor and the capacitor coefficient. And they both think that more conductive is faster, but I don't think so. While the electron itself is very conductive, but when you put it outside, it doesn't move. So I think that it will become slower if it's more conductive.
Okay.
Thank you.
So the reporter, you have 2 minutes to conclude.
Okay, I'm thanks for the other two teams for many good suggestions. Yes, and okay, and for my report, first I want to explain why it will come over to the bottle, because it's because the static electricity. Yes, because it is a static electricity, so maybe it can go through the bottle. So about it. And for the reporter's question is if I put if I put different plastic bottle of it, I know that if the if I use maybe more about it, just it can turn faster if there is no breakdown voltage on it. Because if it is, the voltage will be really low, so it can let it turn fast. Okay, and for the parameters, maybe I just do some, but maybe I didn't say it really clearly. Just for everyone say that I do the degree on it, and I just do some different. I put the electron on different place and maybe more diameters on it. So in the end, I want to say that I just have some little bit didn't my time control maybe need to be better. So thanks to everyone and have a nice day. Yes.
Okay, so question from the jury. So do you have questions? Any questions?
So how close is your needle or your electrode to the side of the rotor?
2 millimeters. Yes.
2 millimeters.
Yes.
Okay, so you fix like this. Thank you.
So which part of your experiment really shows that mechanism is due to this coronal discharge? I mean, which part of your experiment really proves the mechanism is due to the coronal discharge?
Through the coronal discharge, because we use coronal discharge to let the electron into the air, so it can turn really. The static art is observed when motors spin. Okay. It will happen when we put voltage on the electron, and so it will have the high voltage to let coronal discharge happen. Yes.
Did you achieve to go to a desired maximum speed of rotor?
Oh yes.
Because what it is maximum.
Because it will really fast to be the maximum speed, because it have a little bit friction. So if the input force is same, so maybe it will be. And I also use the video. I take the video, and I know that I count out that in the start and in the end, the spinning speed is quite same. Yes. So.
So you drive the machine using your hand, right?
Yes.
Yeah. So how fast do you drive now?
I spin it in two drive in 1 second. Yes. Just.
So you do it manually, and you try to regulate it to two revolutions per second.
I just put a clock near that, so I can know that how soon how fast I spin it. Yes.
So have you tried spinning it faster, say 4 revolutions per second? Have you tried?
Because for round in a second is really fast, but I tried it in one. Yes, one.
So if you do it 1 revolution per second, so does the machine run faster or slower?
Slower. It's slower, and some can be slower more than just half of it, because maybe the friction will affect it less. It's the maybe it should minus the friction of it. So it's if we spin the 1 per second, it will be lower, much more lower than 2 spin in the second.
Okay, I have one question for all of you. Starting from the reporter, opponent, and the reviewer. So is it the voltage important, or is it the field important in driving the motor to move? Is it the electric potential difference, the voltage, or is the electric field different, field strength near the tip? Which one is important?
Maybe the voltage is quite important, but I think the field is more important of it because if I change the different field, it can from stop to over 16, 14,
Okay.
14 spins.
For time's concern, can you?
I consider field is more important, while field is related to force.
Okay.
Yeah, me too. I think the field is most important than more important than.
Okay. Thank you. Thank you all. Okay, you can return to your seat. Okay, time for grading. So, jury, please take time to finish your grading. Okay, so does jury need more time for the score? Okay, how more time for the jury? 再等一下，是吧？ Okay, so for the reporter, Julie, please show your score. Okay, to the camera. Okay, 4, 7, 3, 5, 5. And for the opponent, okay, 5, 8, 5, 7, 6. And for the reviewer, okay, 5, 8, 5, 6, 7. Okay, I would like to invite juries to comment on the highest or lowest score you have given. So for the any reviewer want to comment?
Yes, I think I give the lowest score. Well, probably just my level, yeah. Because but I think the reporter, is trying hard to explain the phenomenon and it did some experiment. But the problem is it's not very clear. The way you show is not very clear. Say that the video that is the key part, whether it is coronal discharge or not, then I think you should at least show it to us. You can see. So that is the key part. And the explanation is not clear because I get misunderstood with the distance. And it's good that you discuss it, you show it. Otherwise, everything you get misunderstood. So those are the 2 points which I the reporting and also the discussion when you do the explanation, try to discuss is not very clear. I just couldn't understand too well what you want to say. Yeah. I think that's the reason why you get no score.
Okay. And do you want to comment?
Okay, I'll give a brief comment. I think the key point is the charge stay on the insulator, but the discussion is always on resistance. It's not clear, so it should be the charge held by the insulators, and it's not clear. I hear that from all field. Okay, so that will be my comment. Okay, so we'll end this round now, and we'll take a break, and we'll resume next. When will be the next? 15. Okay, we'll round the clock.
Okay, time's up.
We challenge number 7, loud voices.
Number 7. Accept. Okay. So the order you have 5 minutes to prepare. So moving to the second.
Okay, accept.
Next stage, yes, accept. Number 5. Accept. Please, reporter, opponent, and the reviewer write your name on the board.
Okay, start now.
Okay, so the reporter takes the floor.
Okay.
Hello everyone, I am Hong Shaoqi from Mingdao 18, and I'm going to present Loud Voice today. This is my outline. First, we talk about the problem statement, and second, we talk about the theory of this phenomenon, and third, we do some experiments, and next, we analyze and have a conclusion. And this is problem statement, loud voice. That means if you have a source of sound and the sound through the cone can be louder. And you have to do some experiments such as the shape, size, and the material of the cone. And this is our theory. The power of the source is the dE by dt, which is a constant because the source of the sound won't change. It's a stable source of sound. And this is the power we got here, A. And A is decided by the area of the receptor. And if the area of the receptor is big A, then the power of A will be P link times 4 pi r and 4 pi r squared A. And this is because that the energy will be spread in a sphere surface. And this A is not a flat A, it's the surface of a sphere. It's one of the ball. And this is a definition of sound intensity, which is power divided by A. And we can get that I not fixed, which means that there's no cones on the source will be this. And this is our theory about the source with a cone. You have to notice that the energy won't change. The energy won't change, and because we have a stable source, and all of the energy will be spread this way. And the big omega is the solid angle, not the field angle, solid angle, which is A of this surface, the sphere surface divided by r squared, which is the radius. And the definition of I, which is power divided by A, and power A will be like this. And we can know that the sound intensity of the cone can be right in this form. So from the definition of the decibel, it's like 10 times log I divided by I0. And we can know that decibel of nothing will be like this, and decibel of the cone will be like this. Here's the main point that energy won't change, but the intensity of the sound will change. What you hear will be louder, but the total energy won't change. And we do our experiment 1. We have to figure out the value of power 0. And this is the definition of decibel nothing. And we take a cell phone with a stable music sound from internet. We have a stable music sound. And the distance between the machine and the cell phone is r. And this is our data. And you can see these formulas can change into this form. So if we do in linear regression, and we can get this line, and you will know that the slope of this line, P0, equals to 1.62. And P0 will be like this. And our experiment 2, measure the decibel while changing the solid angle of the cone. If we put the source of the sound of the phone on the cone hole of the cone, and the sound will be spread in this way. And this big omega is the solid angle of the sound. And the solid angle is the sphere surface divided by r squared. And that is the machine. Distance is r. And this is the data we take. Because decibel with cone, the definition of decibel with cone is like this. And if we change the formula into this form, and we can get the slope of the linear regression will be the P0 divided by omega. And this is the omega we choose. But you can see the omega here is not in a very proper gap because it's hard to control the omega like in 1, 5, 10 20 because it is very hard to do in the material we have. And we can get a slope here. And you can see the linear regression is this line. But you can see the error between the linear regression is very big. And we will explain it later. And this is the slope of the low 6 line. We do 6 experiments from these 6 solid angle. So we can get P0 of cone equals to omega times the slope. So we can know that P0 of nothing equals to 1.62, which we got from the above pages, and it's bigger than P0 of cone. And why this happens? Because the energy won't change, but why will the power of the cone change? And we have to start to thinking about this question. That is, the energy has lost, which when we will discuss it later. But we can see that if the omega increase, the P0 cone will increase. So, experiment 3, we measure the decibel by changing the material of the cone. So we doubt that the collision of the air molecule will cause the loss of energy, because the energy will get onto the cone and go to the outside spaces. So this is our definition of decibel cone and changing to that cone. And we do in 4 different materials, which is paper, tracing paper, plastic, and cardboard. And this is our areal density, which is kg divided by m squared. And you can see, this is the data we got. We got a slope, and the slope here will be the P0 of the cone. So, look at this chart. We will know that P nothing, which we define as P0, and we got an experimental P0. We define it as a P0 cone, and the energy we lost, we write in this form, which is P0 minus P0 cone. And you can see the chart: paper, tracing paper, plastic, cardboard, and the areal density, and the energy we lost. And you can see that if the area density is bigger, the energy we lost will be lesser. So why did this happen? You can see that this is a cone of the wall. And if an air molecule touch the wall, and it will cause the energy loss, because the energy will be passed down the wall of the cone. From the collision formula, we can easily see that if you have a bigger area density on this wall, and you will have the energy you lost will be less. And this is the chart of the energy we lost and the area density. You can see like this. But we haven't found out what formula can be fit in this chart. So we just put it on the dot. So this is our conclusions. If the R, which is the distance of the source and the machine we have, increased, the decibel of the source will be decreased, because you have a longer distance. It's very obvious. And if the big omega increase, then the decibel will be decreased. That means your energy will spread in a bigger sphere surface if the omega increase. And if the omega increase, the delta P will decrease. Because if you increase your omega, the collision of the molecule and the cone wall will decrease. So the loss of the energy will decrease. And we can see that if the area density increase, the delta P will decrease. That means from the formula of the collision, we can easily get this result. So if you want to make the best cone naked, spread a bigger sound, we have to lower down the distance, lower down the omega, and let the area density go up, and we can have a bigger sound intensity. And thank you. This is my report of the loud voices.
Okay, so time for opponent ask questions.
So the report, is that you consider that the way sound waves reflect on the cosmic rise?
What?
You consider that the sound wave will be reflected by the cone?
Yes.
Yes, and do you think that, but in your previous report, you talked about the inverse R squared.
You mean
The energy is proportional to R to negative.
you mean energy will
Yes.
it will increase or decrease?
Decrease by the R, the rate, distance squared. Right?
No, the total energy won't change.
Yeah,
But
I
the
know.
sound intensity.
Yes, and it's proportional to R squared.
Yes.
Inverse.
Yes.
And do you think that it still can be applied when you consider the reflection?
We think it can still, if we consider the reflection.
Okay. You say you play the music sound.
Yes, the static music we found on internet.
What does that mean? Is it a pure tone or?
The same power of the music means the total energy spread by that machine won't change.
So it's not a pure tone, it's just a random music.
Yes, it's just a random music.
Okay. Do you think that it is the thickness of the material that affects the result, or it's other things?
We take the same thickness.
Also, it's the density. I mean,
Density. You mean the?
You mean is it the density, or is it like something else, like stiffness, or like the property of the surface?
If we look at this problem in a formula of collisions, we thought it will be related with the mass of the cone wall. So we think it will be the areal density.
Okay. Can we turn to the?
Okay, time's up. So you have 3 minutes.
Time's up.
Okay, opponent takes the floor.
Honorable judges, ladies and gentlemen, I'm the owner from Team Miracle, and I'm to propose from the 7th upwards. This is a conversation. You are to use a cone or horn-shaped object, and you can use it to optimize the transfer of the human voice to a remote system. I think the most crucial point here is that talks about a cone and a horn, and we should have some discussion between the difference between cone and horn, which didn't appear in the first report at all, and I'll discuss that later. And also, common statements talk about the human voice, and because the human voice consists a lot of different frequencies, and we should do an experiment on the different frequencies as well. And also, it didn't talk about the optimization. Okay. This is the strategy for solving this problem to me. First of all, we should be able to explain this phenomenon, how the cone makes the sound, make the noise sound bigger. And then we should have a steady state and can be reproduced every time. And finally we go to change the parameters and find out which one is the optimal. And this is a report of pros and cons. I think it has nice representation, it has a lot of formulas and a clear problem. But the cons is that I don't think it definitely discussed enough parameters, and it didn't show enough data to prove that this theory is correct. And it doesn't have an adequate theory to me. You couldn't prove that, and you prove the most important part of this problem. And also, he assumed that there's no spread, the sound wave wouldn't spread outside the cone.
Interference.
Oh, sorry. Okay, I'm going to talk about the discussion point that I'm going to discuss later. First of all, it's about the setup. He used a S501 device, a measuring device, and some sort of speaker to play a music sound. I think it's not accurate. I think it's not good to play a music, but instead you should play a pure tone that will be easier to analyze. Also, I have some questions about the device he used. And then he gave three types of data. One of them is about the solid angle of the cone. And here I want to discuss about how he controlled the solid angle, because he seems to have said that he couldn't control the solid angle precisely. Also, about the aerial density. I think that how the material affects the result is not directly related to the aerial density, but actually to how the surface behaves, like whether it's soft or hard. And about the theory, his theory is about inverse square law, but he then considered that the sound is spread outside the shape of the horn, of the cone. And also, he then talked about like the direction of the sound or anything like that. Also, I found out that he doesn't have any error bars in his experiment, and I want to know that can he reproduce those results every time? Okay, I will go to a discussion.
Okay. So moving to discussion.
Time's up.
Okay, first of all, let's go to a setup. Okay, so you use the phone as a speaker.
Speaker you mean?
Yes, it's a phone.
The player.
Player.
So sound.
Is it a point sound source?
Yes, we consider it as a point sound source.
But is it really a point sound source?
Of course not, because we don't have of the technical limited. We don't have
so I think that means that your theory can actually be applied to this sounds more like?
We simplify our theory because the technical limited, but we can improve.
Okay, then about the sound and display. I want to know why do you choose freedom limited?
No, I want to make sure that that is not like music you hear in not a song. It's not a song. It's
a noise, like it's a constant noise, but
yes,
it's not a single.
Not a single tune. Yes.
But why did you choose to use that?
Because we can't really find the single tune on the phone.
And how do you think that it will affect results? About the different frequencies, will they behave differently, or?
I think maybe the different frequency will affect the interference of the sounds, but we consider that in our experiment there's no interference.
Okay. I think that it is still a wrong assumption because there will definitely be some interference when the sound is reflected by the column, and yes, the waveform wouldn't be parallel to each other, so there will definitely be some interference. Yes, so I don't think that is adequate for either for the theory or the setup. Okay, can I go to the relation between the power and the decibel?
Which, the theory part or the experiment part?
The theory part. Okay, so I'm going to ask here, if I take log on both sides, let's go with this line. If I take log on both sides,
Take log on both sides.
so you can put the relation between the power and the decibel.
Yes, not take log on both sides. It's the 10 power. Right.
Oh, okay.
We change into this form.
Okay, I understand. Okay, so we take 10 to the power of this, but on the left here, it will be the pressure. Because the decibel, yes, the decibel is defined as the negative log of the sound pressure. Right?
Sound pressure.
Yes, so on the left here, it will be the pressure. But on the right here, it's P naught is the power of the sound source.
No, the pressure of the sound source.
But you
Here, icon.
okay, but in the at the beginning you talk about like the P is equal to dE over dt, right?
This is the power of the source. It's considered as a static power.
But I'm confused here. So you mean that P, but there are two P's in your theory. One is power, one is pressure.
This means the power that
So P naught is power.
P0 is the power of the source,
Okay, then P is
and
the
PA
pressure.
is the power that got in the surface of our machine.
Okay, then which one is? Then what is the symbol for the pressure? Sound pressure. Or do you have this one?
Here is the sound pressure, and we consider this is the I naught means the PA here, the sound pressure here.
I think sound pressure is the unit is force divided by area. Like
Force divided.
Can use papers from house, no conversations.
okay, I think that you might have some problems about the units here because the decibel is related to the sound pressure.
Sound
but not-
pressure is the power divided by area.
No, but it's not directly related to the energy or the power. But it should be, the power should be proportional to the sound pressure squared. So I think that your theory might have some problems in this part. I think it's not correct, basically. Okay, let's talk about the experiment. Can you turn to the data one? So here you are trying to stay at the inverse spiral force. Okay, Do you have any error bars on this?
No, but we have we have two error bars in our experiment, but we didn't show on this PPT.
And is it really small enough for it?
Yes, it is small enough. But the second isn't small enough, so we did a third experiment to show the delta P of the second experiment. Here, the error bar here is too thick, so we do the third experiment to make sure the delta P that made by the collision of the air molecule.
Can you explain again what this word means?
Here's 6 different solid angles.
Yes.
And
so the graph is solid angle to the delta P.
No, this graph is not this.
So it's still the inverse square.
Yes, we changed the form of our formula into this form.
And how do you explain that it doesn't fit?
What did you mean doesn't fit?
Like the line doesn't fit.
Oh,
well.
Yes, we explain it as the loss of the energy in collision with the wall of the cone.
Okay. Also, so you assume that the loss is like linear, or do you have a theory that
this is of course linear. This is of course linear. We fit this function because of
no,
this.
I mean the delta P, the delta pressure, the pressure loss.
Yes.
You assume that the pressure loss is linear to.
No, we don't think so, because we don't really have a theoretical.
So you can figure out any reason why the line would look like this in your data too.
You mean what line?
Data two.
This line?
It looks like something like this.
Yes, it will look like that.
And why is it?
Because we consider there is no energy loss first.
No, and then what would the energy loss?
If there is no energy loss there, then it will fit this function.
No, what I'm trying to get here is how do you think the energy loss would be related to
the areal density of the cone?
No, not the areal density, but the omega. The solid angle of the cone. Because if you get the equation, you should be able to predict that line, right?
Yes, but we don't have the expression.
So you just have the expression to that. And that also As we here we talk about the aero, I think that aero density is a very then same network effect.
I think we think that the error that in this chart is caused by the loss of energy.
Yes, and the loss of energy is like positive related to the aero density.
Yes.
But to me, I think that the surface, whether the surface is soft or hard, is more important than the aero density. Like if you use
you mean
like
soft or
yes, soft or
so
hard.
Can you explain it in explain the soft or hard in the physics way?
Maybe
we explain it in the collision of
maybe a K value would be okay, the training constant would be bigger or smaller.
You mean the bigger or smaller?
Like when you crash, when you
harder or softer?
Yes. When you push it, the force it would go down more fast. I think that is the thing that is related to the delta P.
So
but not the aero density.
And so you think that the energy that go into the wall.
Okay, there are still some discussion left behind about like I don't think you investigate this in the right direction because you then talk about the cone, the comparison between cone and horn, right? And then you didn't discuss the frequency in human voice. That is what the problem is.
Time's
up. So the opponent, you have 1 minute to summarize.
Okay, I discussed about the recorder's setup first, and I found out that he used the speaker that he used couldn't be assumed as a point sound source, but he still used it and assumed that the energy proportional to inverse R squared, and I don't think that the CV is precise. And also, I talked about the
the thing that he played a sound that is not a pure tone, and I think it will make it a lot harder and a lot harder to explain, because you will have to consider like a different frequency will behave differently, and also I suggest that the recorder teaching.
Okay, so reviewer, you have 3 minutes for questions.
For the recorder side, the first thing I would like to ask, what kind of basic concept you use to explain the display your weight? Is it interference or reflection? Or other explanation?
To explain this phenomenon,
Yes.
more than interference and reflection.
So
I think these two is the main reason that cause this. That these two is not the we ignore in our experiment, and we think that the sound will travel in a spherical surface.
Okay, and so our second question. So in turn to page 8. Could you give a clear explanation of the coordination of what the x-axis and y-axis is?
Because the function of this line will be the linear regression of this. So we got the y as the this and x as this. So the slope will be the p0.
Okay, so, and the last question would be, what's your last initial assumption? Is that the energy will decrease or not?
You mean energy will decrease
In the yes.
At first, we considered that the energy won't lost, but we found out that that in the experiment we had, there is too much error. So we consider there is an energy loss because of the collision.
Okay, thank you. And as for the opponent, one question to ask. So if today you are going to measure the wave that propagates through the horn, do you think it is possible to measure every single particles, air molecules inside the horn? Do you think it's possible?
Oh, that's definitely not. But I don't really understand what you're saying. Sure you can.
So do you think on doing this research would that be efficient to measure?
Trying to measure the sound pressure everywhere.
Yes.
You mean like distribution?
Yes, the sound pressure.
Yes, definitely. Maybe the proponent will get like the relation to prove that the relation is radial symmetrical or not. Something like that.
Okay, thank you. I get your point.
Time's up.
Okay, so the reviewer, you have 2 minutes for preparation.
Okay, the reviewer takes the floor.
Okay, so honorable juries and fellow participants, I'm honored to present Big Long here to talk about and review this topic. So first of all, was it connected? Okay, so turn to the first slide. Thank you. Alright, so first of all, let's look at the problem statement. It asks us to use a simple point shape to do the investigation of the loud voice. And so the reporter gives us many clear, so the reporter gave us a clear phenomenon and told us what the phenomenon will be. And also she had did some formula regarding to sound intensity and also give us some clear definition and charts among it. And as for the experiments, the change factors including solar angles, material densities, and their setup. The most importantly, what I want to point out is that they use cell phone, claim numerous frequency as their frequency generator. And as for their conclusion, this is what they got. Mostly, R increase and U will decrease, and also some relevant formulas. So, and next, we're going to talk about their advantages and disadvantages. So because they have done precise things on talking about their advantages on those phenomena and theories. So at this point, we believe they did give us a good impression. However, there's one thing that they might not consider is that they kind of contradicted to themselves one after another, because first the assumption is the energy won't increase, but at last they find out actually the energy does increase. And second of all, they use absolute reflective things to explain the whole phenomena. But however, we have to bear in mind that if we're using this, if it was absolute reflect, the momentum will be stable. So that means there won't be any energy decreases. So perhaps at the very first place, they have made some errors among their researchers. However, at last, they still give us a quite clear vision of how this might work. As for apart from opponents, they did give some excellent question advices, like including what's your frequency generators? Is it that a plane wave? And is it a dark wave form? Or is that something that very hard to imagine? And also they show a great understanding into a topic. But however, also there's one thing that I want to talk about their pros and cons is that, this is the page. The summary and reporter are clear, and maybe they are a bit too focused on self-opinion. They should be more focused on the reporter side and have further discussion on their current investigation and all theories they use. And so next we're going to go into all their clashes. So there's one thing that I want to point out due to time constraint is that the air molecule couldn't be absolute reflection, and also it could be it's impossible to track every single particle. So at this place, we believe our opponent did some mistakes. However, they do have a great sense on understanding the problem. They give us a very clear vision and a great discussion with the reporter. So basically, that's all my report. Thank you very much.
Hands up.
Okay, the reporter, you have 2 minutes to conclude the remarks.
I want to say that the collision that caused by the air molecule and the wallpaper is by the if the air molecule touch this wall, and this wall cannot be seen as a very huge mass, so it will absolutely vibrate or just get some energy from the air molecules. And from opponents, we have limited machines, so we cannot do these experiments in very good environments. That is the thing that we can improve. And from from both of you said that the error bars that we should put on the PPT. So we can say that this chart, the error is small, and this chart, error is big. So we have to do another experiment to talk about the error we made in the second experiment. And this is all of my remarks. Thank you for listening.
Okay, so we'll move into the question of the jury. So, you guys, so the jury has questions?
Yes, I'd like to clarify. I think your opponent also asked this question. So when you compare the loudness you get between the nothing and the cold, does the loudness decrease or increase?
The loudness increase with the cold. Yes, but the energy, the total energy won't change because the concentration of energy.
No, because you have measurement. You have measurement for nothing, right? Then you have measurement for that with the cold.
Yes.
So if you compare the two numbers, which one is bigger?
Of course, it's with the cold. You mean the sound intensity?
Can you show me the video?
Here?
This is nothing, right? So what's the number? What is the number?
No, this big omega must be smaller than the...
No. You take two measurements, right?
Yes.
One with nothing. You take a measurement. One with a code. So you make measurement. So can you show me those two numbers?
Here. The P0 of the nothing. And P cone is smaller than the P0.
So nothing is bigger than the P code, right?
Yes.
So with the code, you get quieter. Without the code, you get louder.
No, that is not louder. That is the some pressure. That is some pressure.
I don't care. That represent something that we can hear. If this number is big, then it means it's louder. Is that correct?
No, I think that what we can hear is.
All right. Okay.
Question from jury?
So one factor of this cone shape, of course, is the length of the cone. So what's the effect of this length of the cone?
We take the length of the cone.
So you given
yes,
very
we didn't measure.
Questions? So is the intensity related to the loudness or the power related to the loudness? You hear something?
I think it's the intensity related to the loudness.
I have one more question. So in your previous page, maybe page, this one. So in your experiment or in your data, are you sure that this result is due to the error? Because you mentioned that the error bar in this experiment is big, but I'm sure that it didn't give you some. This data might give you some physical insight.
Yes. So we got this. The air molecule must pass the energy to the wall of the cone. So we do another experiment of the areal densities and the material.
Can I have another question since it's the time? So when you say that you vary the solid angle, how do you vary the solid angle?
Solid angle?
So that you have a graph.
You mean solid angle?
The graph you have.
The graph. This one?
No, the data.
The
This
table.
one,
The
this
table.
one,
Yes,
one.
this one.
Yeah. How do you vary the omega? You use different cone, or you use different lengths or different angle?
And the omega is the ratio of the sphere face of the cone and the radius square.
So how do you vary it?
We measure it like
different faces, or you use a different code?
we keep the radius same.
Okay.
So we take the sphere bigger or smaller.
So you use different code, right? Different code. One is like this, one is like this, something like that.
Different felt angle.
Because solid angle is longer. So can you tell me what it did exactly? You use a different code?
I think so.
Or you use a larger code?
Okay, so time for the grading.
Do you need more time? Okay, so I think we are all ready. So, okay, score
Is camera ready? Camera is that way down. Okay. The score for the reporter. 2, 9, 4, 4, 6. Okay. And then the score for the opponent. 8, 6, 6, 8. Okay, and then score for the reviewer. 4, 9, 6, 7, 7. Okay, so let's have the score on the board. Okay, again, I would like to invite jury with extreme score, extreme high or extreme low, to comment. Okay, I'll start first. I give reporter a very low score. First of all, your presentation is not clear. You demonstrate how you do the experiment, and then you show a lot of data, but it's not clear. Okay, how is it related to the phenomenon? Okay, and then you answer the question poorly. Okay, especially to jury questions. You should give a very definite answer. Okay, and you sometimes confuse the audience with some pressure, power, and without clear definition. Okay, so that's how I give you 2 points. Okay, both on the presentation and the answering questions. For me, to the opponent, I think to my point of view, you ask very pointy questions to all the result presented here is not clear present or doesn't address the point. I think you try to lead a point to the missing points in the presenter's, reporter's presentation. That's why I gave you very good scores. Okay. So other jury like to comment?
I give you a very high score because I feel that although your presentation is not perfect, you didn't demonstrate the data well enough, but probably my personal opinion, I think it addressed the question for this debate. You try to investigate how the sound propagates into the space without cone, how the cone helped to enhance the intensity in the cone. And then also the size of the cone changes some angle, and the results is pretty well. Although even fully explain why the relation you get is not linear. Also identify how the material will affect the result and then give a decent explanation. That's why I see.
Other jury comment? Okay, so we'll end this section and we have 15 minutes. How many minutes of break? Okay, we'll take break now and the clock will show how much time.
Left 12 minutes.
12 minutes break. Okay, we'll take 12 minutes break. Stage 2, round 3. So the opponent, you have 1 minute to challenge the reporter.
Okay, stop.
Okay.
We're going to challenge soy sauce optics.
So number 10, soy sauce.
Number 9.
Number
Number
9,
nine.
soy sauce optics. So reporter, you have 1 minute to respond.
Hands up.
Okay, reporter.
We accepted.
Okay, so
Accepted.
number 9, soy sauce optics. So the reporter, you have 9 minutes to prepare. And please, the reporter, opponent, and reviewer, write your name on the board.
reporter takes the floor.
Honorable judges, ladies and gentlemen, I'm the reporter from here today. I'm going to report on number 9, suicide topics.
You may want to speak louder.
Okay. This is the problem statement. The problem says that we can use a laser beam and send it past a thin layer about 200 micrometers of soy sauce, and then we'll observe the thermal lens effect. And we need to investigate this phenomenon. And this is a picture of the thin layer of soy sauce that we took from our experiment. Okay. First of all, we're going to show you what is the thermal lens effect. Okay. This is a medium. And then we're going to send a beam of laser into the medium. The beam of laser would act as two things. First of all, it will act as energy input. Also, it will act as an indicator of the thermal lens effect. The laser goes into the medium and it gets absorbed. And it will conduct the heat, and then there will be a thermal gradient here. And since the soy sauce will expand when the temperature gets higher, the refractive index would also be smaller when the temperature gets bigger. And therefore there will be a refractive index gradient over the soy sauce layer as well. And that would cause a thermal lens to happen. And the way we see this effect is that the laser beam coming into the layer of soy sauce will get wider or maybe narrower because of this lens. So we can tell whether the thermal lens effect is happening by looking at the radius of the laser beam coming out. This is our setup. We use here is the laser over here, and we pass the laser through a convex lens first to concentrate the power. The focal length is about 143 millimeters. And here is the soy sauce film. We note this lens between the laser and the contact lens to the soy sauce film as C1. And also, we ignore the distance between the laser and the contact lens. We keep that as about 0. And then this is the luminance sensor. This can sense the luminance in lux and we place it D2 away from the soy sauce film. And we test the thickness of the soy sauce film. And it is about, we make 2 pieces of soy sauce films, and the thickness is either 216 plus or minus 3 micrometer or 405 plus or minus 3 micrometers. And then in our experiments, we can move the luminance sensor and then test the luminance at different places along at different places in this plane perpendicular to the laser. And then we can find out the distribution of the light, of the brightness. Here we're going to discuss about the Gaussian beam. Okay, in the normal laser beam, the intensity behaves in a Gaussian distribution, which means that okay, this line is a laser beam, the thing here, and this is the position there. The laser would have a waist, which we call W0, and then in this cross section, it will look like something like this. The laser is coming from the right from the left to the right, and this is a cross section. And the cross section would have a radius W. And if we plot the luminance along the R axis, we should get a Gaussian distribution if the laser is Gaussian beam. It's a Gaussian beam.
and we'll define the radius as where the intensity reaches the maximum intensity divided by E squared. And we call this length to be the radius of the laser at this point. And then if we measure the intensity in our experiment using the illuminant sensor, we can tell that the Gaussian really fits the data. So we're going to use this method to determine the radius of the laser at different positions. Okay, because we know that the N over dt is negative, means that the higher the temperature is, the lower the refractive index of the soy sauce is. We can know that in the middle, the temperature is greater, so that the refractive index is lower, which is the same in a concave lens. In a concave lens, the middle has a shorter thickness, which means the equivalent distance in air is shorter, and here the equivalent light distance is longer. And in the soy sauce, it's the same deal, because in the middle the refractive index is smaller, on the outer part is bigger. So if the thermal lens does work, the soy sauce film would actually act like a concave lens. And we can know that, citing this paper, we can know that when the concave lens is placed before the focus of this convex lens, then the beam radius would actually be smaller than what you would get without the concave lens. But if it's longer, the D1 is longer than the focal length of this lens, then it will be bigger. So we tested so we do the experiment here. The x-axis is D1, which means the distance between the laser and the soy sauce film, varying from 0 to 60 centimeters. The y-axis is the change rate of the radius of the laser. 0 means the radius didn't change at all, and positive 0.6 means the radius becomes 1.6 times the radius than when there's no soy sauce. And here you can see that the radius is actually from negative into 0, but here and then to positive, and then going back down to 0. And this fits the theory before, since the focal length is about 15 centimeters, about here. And here the soy sauce film, if it behaves like a concave lens, shouldn't concentrate or spread the laser beam at all, which is what we saw. Here the white ones are water, and these are dishes, and the lighter brown one is the thinner soy sauce film, and the darker brown one are the thicker soy sauce film. You can see that the thinner film, because it absorbs less light, therefore it creates less thermal gradient. The effect is less significant, whereas the thicker film has a more significant effect. Okay. Also, we try to change the power of the laser, because as we know, if the power of the laser is bigger, the thermal gradient would also be bigger. That means the effect would also be more significant. Here we tested two kinds of lasers with power 1.39 milliwatts and 9.67 milliwatts. And you can see that the stronger the laser is, the higher the greater the effect is. And then this is our conclusion. We cited the paper, and we can know that if we place the laser, the soy sauce film further away than the focal length of the concave lens, then the laser will be concentrated. The
width of the laser would be smaller. and we place it further, sorry, it's the opposite, it's very much. We place it further than the focal length, the laser concentrates. If we place it shorter than the focal length, then it diffuses. If we place it on the focal length or at a far enough, at a far point, so that the power and the energy transmitted from the laser per area is too small to cause any thermal gradient, then the laser doesn't concentrate or diffuse at all. So the width stays the same. Okay, so here's the conclusion again. We checked about the absorbance by changing the width of the space-time film, and we see that the bigger the absorbance is, the more significant the thermal laser effect would be. That's the same to the thickness. And also we check the power of the laser. The higher the laser power is, the more significant the thermal effect will be. And yes, we'll check. Yeah. Okay, that's fine.
Okay, so the opponent has 2 minutes for questions.
Okay, please turn to page 2. So is this your experiment and should by you? This picture. Okay, and turn to page 3. Can you click more? So you can show the whole slide. Okay. So is it so it's a medium will become a convex lens or another lens will cause the laser to divergence. Which one? Is it divergence lens or convergence lens?
Or divergence.
You believe it will always be a divergence lens?
Well, it behaves like a divergence lens, but it doesn't always diverge the beam.
Okay. Then turn to page 4. So while you're moving the sensor, the illuminant sensor, I mean like why you're moving it?
Because we want to know the distribution of the illuminance.
So is it impossible to like measure the whole intensity distribution on beamwaves?
How do you mean?
Is it impossible to measure the intensity of the distribution of the intensity at once? You need to move that.
Yes, we have profile, right? Yes, because we only have this illuminance sensor.
Okay, and turn to page. Excuse me. Turn to page 6. So have you, since it's only talking about using a laser beam to go through a soy sauce lens, have you ever tried other kinds of laser beams? I mean, with the different.
Because most laser beams, most commercial laser beams behaves in this way. It's a special mode that the laser beam has, and it's always like most of them are Gaussian beams.
Thank you.
Okay, time's up. So the opponent have 3 minutes for preparation.
Okay, opponent takes the floor.
Okay, so honorable juries and fellow participants, this will be an opponent review of the T miracle soy sauce optics. So first of all, this is a problem statement which they had just talked about, and here I want everyone to focus on it was asking using a laser beam. It doesn't ask which kinds of laser beam. Okay, and second of all, after it, we're going to have a brief summary and a comment of the opponent. So in their presentation, we can learn that the theories including thermal lensing and Gaussian distribution. However, at this place, the Gaussian distribution are lack of explanation. And as for the setup, they use soy sauce laser beam photo detector, which are moving all through that sample, and also they use we didn't see they use an infrared camera to measure the heat, the change on temperature of the sample. So at this place, we wish to have further discussion with them about the thermal lensing, which is a crucial part of this theory. Instead of their parameters, including the power of the beam, solution, and the thickness, we believe they did a good job on finding the parameters, since we also find some difficulties doing this very experiment. And as for their experiment, there's lack of clips and pictures of the experiment. So we'd also like to further ask them to show some of their clips of their experiment later on during the discussion session. And as a result, they believe that the higher the absorbance, higher the power of the beam is, and the higher the thickness the sample is, the thermal lensing effect will be even stronger and more obvious to be observed. Okay. So, and next place, we're going to go through their pros and cons. They did a well presentation on this a little difficult problem, and also they have a good equipment utilized. And as for the next, however, on their chart we didn't see the tendency and all those kind of they didn't show a very clear trend on their chart. And also we're kind of curious about size of each particles. And next is about their parameters, since they only use soy sauce and water. We'll also expect to see why they use soy sauce. I know the topic asks us to use soy sauce, but why soy sauce? Are there any other solutions that can compare it to a soy sauce? And next, the meaning of the error bar of their result of their experiments, of their chart, are also something we'd like to have further discussion with them. And lastly, they also explain about. Lastly, they did a well-rounded experiment, and they did try their best to do the theoretical explanations. However, we believe that they had lack of consideration of the color, the wavelength of the laser beam, which is also crucial to this effect. And second of all, is the angle they shoot the laser beam into the sample. And further of all, is that and further of all is the result, because they didn't have we only got only a trend of them, which is only the absorbance, power, thickness that will cause a more thermal lensing effect. We believe there should be something more than that. So let's wait for the discussion part and let us to have a great discussion upon this topic. Thank you.
Okay, so we'll move into discussion.
Okay, so since you have mentioned that sometimes it will basically act like a concave lens, right? Can you explain why it acts like a concave?
It will always act like a concave lens, but it will sometimes diverge the laser beam in some exponential.
So sometimes it diverge the laser beam, and it will act like a concave lens, right?
Yes, always act like a concave lens.
Okay, and second of all, can you describe what's a Gaussian beam and Gaussian distribution? Can you give us a further explanation on that?
Okay, the Gaussian beam is in this picture, these two lines represent the radius of the laser beam along that axis, which is the axis the light is propagating. So laser is going in this direction, and then the width of the laser beam is getting bigger and bigger because so this is how the laser behaves.
So if today we're using a laser beam, like It's a laser beam. No. Okay, so if today there's a laser beam, and let's imagine that there's a space with infinite infinite length. And when we use this laser beam stroke through it, what we'll assert is that the laser beam will diverge all the way. Is that correct?
This angle is actually really small.
That's really small.
Yes, it's actually really small because the laser wouldn't diverge that much if it's on its own. There's no length at all. The angle is actually really small.
Okay, thank you. And if you're looking on the Gaussian beam, so can you describe what does these matrix means here on your presentation?
Yes, those matrix is
the latter page, the previous page. Yeah, page 1. Yeah, what does this matrix mean?
Yeah, those matrix means that it's using matrix optics to measure to calculate the theoretical width of the the laser beam. Okay, these four matrices representing this is the distance. This is how the light will get bent or manipulated after traveling d2 distance in air, and this is d1 distance in air. And these rules are how it will get manipulated when traveling through a lens with focal length of negative f or FTH. And this FTH is the focal length of the thermal lens.
Oh, okay, thank you.
So it's just a calculation.
Calculation. So how about the ABCDs right here?
Oh,
what does it represent?
Like we can use this to detect how the width should behave. How the width, we can think the width from this part, from the starting part of the laser to whatever the z-axis is.
So could this formula apply to other like normal concave lens, right?
Yes.
Okay, thank you. And as for the turn to page 17, which is the conclusion of your initial presentation. The next page, please. Oh yes. So since you said the thicker the layer is, the more obvious the more less effective.
Yes.
So let's imagine that there's a pool of soy sauce. So imagine there's a pool of soy sauce, and then today you use a laser beam, you go to the soy sauce. What might happen?
Well, I mean,
You're going to observe a very clear
it will
thermal
be,
effect.
No, I mean the thickness effect is to a certain degree.
Just a
Because of course, if it's like a pool of laser, a pool of soy sauce, you shoot the laser in it and will get absorbed right away. You can see everything.
So you can, okay.
Yeah, so of course that wouldn't work.
I'm talking about that. How about you thinking about the color? Does the color of the soy sauce affect this?
You mean
And under what parameters can you give us?
you mean like whether we're using a red laser or green laser would it
No, I
affect
mean
how
the
many?
color of the solution, of the sample.
I don't think so. I think only the absorbance. I guess what you're asking is like the absorbance, right?
Yes. And as for the next thing, so since today you're using a soy sauce to do that lens, and you have also used water. However, it is obvious that the water doesn't have that clear thermal lens effect,
Yes.
or there are even no thermal lens effect on
Yes.
water. So there's no thermal lens effect in water, right?
Because the absorbance is pretty small. It's almost zero. You wouldn't absorb any laser, so you wouldn't create the temperature gradient.
But based on your previous, which are your initial thermal lens effect, your definition. So let's today imagine like there's other liquids, such as actually like in a piece of glass. It could be it. So if today I want to turn this, could I use a laser beam to turn it glass?
Well,
into a
you
convex?
can, but it needs a really big power.
So if today we use a very big power of the laser beam to go to straight through a layer of water, will it happen after the
Yes,
effect?
it is possible, but we don't have that kind of laser. We don't have those kind of about 10 milliwatts.
Okay.
What we got.
Okay, thank you. I think we got your point. And as for the next session, let's keep moving on to page 13, parameters of observance. can you go to the next page? The next page. The next page. No, the next page. Next page. And next page. Okay, this one. So, since you're talking about D1, so you measure D1 and the focal length together, right? I mean, so when you're measuring the whole thing, you know how's the length of D1, and also you know the focal length of that convex length, right?
You mean the sweet and you mean the convex?
Yes, the convex
phase there.
Yes.
Yes.
So I'm curious about what does that convex thing do right there? They have certain functions?
Okay, let's draw. Well, like that, yeah, right. Concentrate the
Okay, you need to raise your voice. Yeah, the tree has to listen.
This is the convex lens, and this is the laser. And the laser beam going into the lens and concentration and not focus and the focus. And then touching the focal length to diverge.
And then you put a sample of suicide.
Yes, you put it either here or here. It will pass different results.
Okay, and how about if you remove this convex lens?
Okay, the reason that we use a convex lens is because that the laser on its own is like the power is not enough. So we need to concentrate it and make it in a smaller radius. So around the focal length, the effect will be stronger.
Okay.
That's why we use it.
Okay, thank you. And you turn to the previous page. I want to know how you get a conclusion with only one result graph, this one. And do you have like any clips that can show us in the past 2 minutes?
Clips,
the clips of your observation, and also how you got this chart.
I think we only need pictures. Why would we need clips?
So you don't think clips is, so you don't need clips to prove it, you don't need to show us a chart.
I can show you the picture of the laser. I don't have the pictures, but I believe that showing the pictures would help, but I don't have pictures now.
Okay.
The pictures of the laser dot.
Okay. Now I just want to see the exact of your experiment. Okay, and also, what do you think that may happen if we change the following variables, such as the different wavelength of the laser?
Wavelength.
So today it seems that you only use like the green laser. What about if today you try other kinds of different lasers?
Well, actually,
this might be the last question. Yes.
Actually, I don't think the frequency will affect the result at all. But there's one thing that would be affected because we're using a sensor that is detecting the luminance, and the unit is lux. And lux is not a definite intensity unit. Like the definite intensity unit would be watts per meter. So.
And also, I would like to ask you. So, is a thermal lensing effect happens at the exact moment when you through the laser beam through the sample?
Almost the exact moment. Like the time period is very small.
So then, how can you move that illuminate sensor around? There should be some time lapse, right? So how can you? I mean, like
we move it under, and we get stable, and then we move it.
You move it stable.
Yes.
And
we
then
are detecting. We're always detecting a stable configuration.
Okay.
Okay. So the opponent has 1 minute to summarize the discussion.
Okay, so based on our discussion about this, we know that the reporter did have a clear sense of the whole effect, and also we'll try out their efforts on trying to explain some of the formulas that maybe other people won't understand at the very first point. So based on their experiment, let's give a quick summary. So let's look at the, okay, I have 30 seconds left, but I'll try my best. So they had a comprehensive experiment with more than 3 variables. However, the more consideration of the variables are desired, such as wavelength. So maybe that's the future prospect. And also, you did a clear explanation, and I don't need to mention how you did your experiment. However, we still really want to see how the whole experiment going on, since there's lack of flip and interest. And that will be our remarks. Thank you.
Okay, so reviewer, have 3 minutes for questions.
Okay, I want to first ask the reporter that you did measure the D1 and you did measure the D1, and how about the D2? Is it will cause?
Well, it will cause the like it is correct. But further to get the bigger we can change the control the total length.
Oh, and I want to ask why this will be go out more and before it touches the lens, before it touches the divergent lens.
The counterpart the width is will naturally go up and down because this is a special mode of the electromagnetic wave propagation. There's some mathematics behind the lasers. One of the most common stable laser AP. So we assume that our laser also behaves like this. So this is just something that we can get for use by the Maxwell equations.
Also, you think if also even though there is no any lens in here, it will diverge.
Yes, but it diverges really slowly. Really slow compared to like when you put a lens there.
Oh, okay. And I want to ask opponent, why do you so confident about the question? Why do you so happy or?
I really have some answers of all my conclusions about this topic. So, like, I really want to have a discussion with other people. Yes. So, but maybe next time we try some questions and really get to some my physics concept.
Okay, so the reviewer has 2 minutes of preparation. Okay, reviewer takes the floor.
wait for the. Okay, and this is our PPT. And this is the problem statement. And yes. Okay, and this is the overview for the reporter. And I think their purpose is very good, and they did a very difficult experiment, I think. So their setup and the equipment, I think, is very, very good. Yes, and their theory, they use thermal lens effects, and they have the Gaussian distribution. But I think the suggestion is they could speak more clearly or maybe louder. And there are too many pauses during his report. Okay, and this is the overview of opponent. I think you speak very clear, and you did focus us on the main idea you want to talk about, and you look very confident. Yes, and this is your discussion. First, opponent asks the reporter is always a complex lens, and the reporter says yes, it always. And opponent also asks what's the matches on the reporter's report is, and he replied it's just the code, so we don't need to understand it or something. Yeah, and opponent also asks if the thickness is very big, like a tank will be here, then what will happen? Well, then the reporter says it has a range, so we can't put the thing as so big. It must be very thin, like their experiment units in UN. Okay, and this is another discussion. Opponent wants to ask what will the laser beam's color effect, and reporter thinks this effect will be considered in the solvents of their theory. Yes, and opponent also asks will the water have thermal lens effect in this phenomenon? And the reporter says it will, but if you think it's too long, you should have a very big power to observe this phenomenon. And discussion 3. Opponent asks, do you know the focal length of the convex lens, or you have a question? And the reporter writes some figure on the blackboard.
Time's up.
Okay. So the reporter has 2 minutes for concluding remarks.
Sorry for not being very announced, but I'll draw the observations. I'll show you how we take the measurement. We take the measurement for Gaussian mean. I showed in one of the pages before, and let's take this is when there's no it's only laser. Then when we add so example, it might be something like this. It's still a Gaussian curve, but it's lower. It's a lower Gaussian curve, and the radius is bigger. And what we use is the radius here. Okay. And some questions the reporter asked about the temperature difference. We didn't use the infrared camera to the temperature difference because the temperature difference would be really small, like about 21 degrees. So we couldn't directly measure that. And we also discussed the unstable states before the whole system reached the temperature equilibrium. Like we can discuss whether it is still conducting because the delta T is as well. It's also maximum. Okay, and what I'm going to say is that the Gaussian beam here is not an assumption of us. This is like a mode of lasers that can be derived mathematically from the Maxwell equations, and this is one of the most common form of laser behaviors that you'll get in commercial lasers. So we assume that is what we get in all lasers. Okay, and about matrix, the ABCD matrix is just a mathematical way that we can try to calculate the how the laser behaves.
Okay. So, question from the jury?
I'd like to know this report is in your experiment. You show for D1 less than the focal length, you get a negative change of your beam width. In your experimental data,
yes.
You show for this D1 less than this focal length F, you have this negative
Yes.
ratio of this beam width. So can you comment more on that, and also I'd like to hear the opinion from this proponent and also reviewer.
Sorry, wait. Okay. This sorry. That's when the second for the.
Yes, it's okay. So which
Okay, so yes, this is a diagram we get from this paper, and it shows us that it also uses a convexance here. And this is the thermal length, the Swiss film, and we can see that when the Swiss film is put closer to the like near is it shorter than the focal length, and it will converge on the other end. A bit longer and focal length will diverge on the other end. So that's why it sometimes is negative, sometimes positive.
Yours? You want to comment on that?
Oh, yes. Because you guys just talked about, you said it will act like a convex lens. Concave side. It acts like that, and I think you do know what equals to the refraction index. You know,
No, a comment on the answer,
Oh.
not your questions.
Because that will be affected by also the refraction index and also the right hand temperature. And you said sometimes that, well, bigger than 0 equals 0 and smaller than 0. But here it doesn't have very clear explanation, and also the data to show us that you're very certain about your experiment shows us about this.
Comment on the two phenomena. The concave lens will diverge and converge the beam. Maybe the reviewer can answer the question.
Oh, I think it's very reasonable because it says the laser beam will be the radius will be big and it will be big for itself. So this is very small, but if you have the lens on it, it will be big. So I think it is very reasonable for the 0 or positive or negative radius they measure.
Okay. So other questions?
You use two different thickness of layers to do the experiment.
Yes.
How do you prepare such proof?
And how do I make those?
Yeah. How to determine the thickness?
We use two pieces of like plastic sheet on two sides, and then we put some attachments in between, and so to separate the two films, these two are plastic, and then we stick it together, and then we put the soy sauce inside, and then we measure like how thick that is. So So basically, it's two sheets of plastic with some distance in between.
Following question, so how do you measure thickness of the material? Is that by
We
centimeters?
use the calipers and
By parameters.
I have a question for the reviewer, opponent. That you seems to be very persistent about the color of the solution. So let me ask, suppose the color looks like red, and I'm using a red laser. So what do you think the effect of the divergence, the effect of the thermal lens effect, is it bigger or small, as compared when we use say, a green laser?
You mean the wavelength of the laser beam?
The color, if the color of the solution is the same as the laser. So, as compared to the color of the solution is different from the laser. So, which one has the stronger effect for the thermal lens effect?
But so since today, if the color were the same, I mean the beam and that sample, the color was the same. So basically, it will just reflect all the same color. So we believe that the previous one we can observe. I mean, observe by our naked eye more clearly.
So which the lens effect, thermal lens effect, which one is bigger? Same color or not the same color?
Same color.
Same color, we have a stronger thermal lens effect. That's your answer.
But you mean in a sense? Oh yes, still same.
How about the?
I think it's the different color because that way it will be useful. Otherwise, it will pass through both.
How about the reviewer?
No, I think it's the same as the reporter.
Okay, just for me to clarify, when you do the measurement, like as you move, I think
The sensor.
no, not sensor, you're trying to measure the variation of the beam west. So is the focus still maintained at the point source? That's why I'm not clear how you measure the impact. Can you show the measurement setup? Okay, time's up. We'll hypo grade.
Okay, so does the jury need more time? Okay, so we show the score now. So for the reporter, okay, 5, 9, 5, 6, 7. And for the opponent, 5, 8, 6, 7, 7. And score for the reviewer, 4, 7, 2, 4, 5. Okay, so I'd like to invite juries with extreme scores comment on the how you give the scores.
Basically, it's the reviewer. They just seem to do the right job because it seems there are many points that are missing. And there's something that is, you should look at comments on other people's way happiness. That's not a way. And you didn't use your time, I guess. The key point that you didn't point out. Next time do that.
I like that you presented the different views, but you did not present your own view about the discussion. Okay, that's something you can do. Others?
May I point out that that student, you should not sit on the chair. So the sitting there is no good. Okay. Sit on the back of the chair. The other guy, I don't know which one.
Okay. Okay. For your health. For your health. Okay. Okay. I'd like to comment on the opponent. I think you are very active and positive attitude, but somehow the point you're addressing is not yet essential to the reporter's results. Okay, so for example, I think the Gaussian mean may not be the most important issue unless you want to discuss about temperature gradient distribution. So something like that, and the ray tracing, you know, it's not the major part of the presentation. Okay, so I think you should focus more on the central points. Okay. If no further comments, we will end the session now, and then hope everyone enjoy your lunch. And thank you, everybody.